Okay, so now we've started with voltaic cells, and we've talked about one of the things that we want to know is which direction that voltaic cell goes, right? So do the electrons flow? They're always going to flow from the anode to the cathode, but when we write out a reaction that has ions in it and we have to balance those half reactions, how do we know which side of that reaction is favored, right? This is the same question that we keep coming back to. When we talked about acid-base reactions, we wanted to know which side of this reaction is favored. When we talked about equilibrium constants, we wanted to know which side of that reaction is favored. And what we're going to see is it's going to be more of the same. Only now we're going to use delta G. We're going to use free energy to figure this out. And there's a couple of equations in here that I'm just going to kind of ask you to just trust me on, because deriving them takes a lot of physics and a lot of math and all that other kind of stuff. And that's not how we're going to spend our time. So there will be a couple of equations where I'll say this is the equation that we're going to use, and it's not entirely clear where it comes from, but when you get to physics, you'll see these things as well. And what we'll do is we'll keep relating everything back to equilibrium and all that kind of stuff. So hopefully it makes sense. Okay, so let's take our voltaic cell, our example. So voltaic cells and free energy. Let's take a voltaic cell where we combine lead and zinc. Okay, so again, we're going to choose a pretty straightforward voltaic cell because this is the first example that we're really going to look at. Right, so when we think of this, of course, we're always going to think of this in terms of half reactions. And so we're going to have two half reactions in here. We're going to have lead 2 plus 2 electrons gives me lead 0. And we're going to have zinc goes to zinc 2 plus 2 electrons, right? And we have our reduction here, and we have our oxidation here. But remember that this could also go the other direction, right? We could also write this out with lead on the other side. So if we look at the reverse of all these reactions, the reverse of the lead reaction, lead half reaction, would be an oxidation. The reverse of the zinc half reaction would be a reduction. So that's going to be important here in a minute. So the question is, which direction does this go, right? Do we go from lead 2 plus to lead, or do we go from zinc 2 plus to zinc? Which, when we have our voltaic cell, right? So remember our voltaic cell, we've got our lead over here, and we've got our zinc over here. We got our zinc bar, our zinc metal there, and zinc 2 plus. In this wire that's up here, here's our salt bridge. Do electrons flow from lead to zinc? Do they flow from zinc to lead, right? Which one of these is our anode and which was our cathode, right? Have we drawn out this reaction the correct way here, or do we need to reverse it? The way we figure this out is with delta G, right? So remember that if delta G is less than 0, our reaction is spontaneous. That means the reaction flows in that direction. Okay, so how do we calculate delta G? The way we calculate delta G, and this is the equation that I warned you about that I'm just going to kind of pull out of thin air, is we take delta G is going to equal the number of electrons, so N equals the number of electrons in the balanced equation, F is going to be the Faraday constant, right? The Faraday constant is 96,500 joules over volts times moles, right? So the number of electrons is going to be in moles. The Faraday constant is in joules over volts times moles, and then the E, the epsilon rather, is going to be the potential of the cell in volts. Right, so moles and volts are going to cancel out here. We get our delta G in joules. All right, so all of these things are new. right? We've never really used the Faraday constant before. We've never used cell potential before, any of this kind of stuff. So where does this all come from? What does it all mean? Basically, what this boils down to is we can measure the cell potential very easily. We just put a voltmeter on our wire in between our two half reactions and figure out what the potential is, right? How much do we get going across that line? So what we're going to use is we're going to use a standard set of values for these half reactions. So each of these half reactions, right, we're going to find a value for, and these epsilons are going to come from a table. Appendix 11 in the Top Hat textbook, or there's a table in chapter 18 that lists all of these potentials, right? So you can look up lead plus 2 electrons goes to lead, lead 2 plus 2 electrons goes to lead. You can look up the potential for that in this table, right? The thing about these standard potentials, right? So standard potentials is that they are always going to be of reduction reactions. So when you look this up in the table, you're going to see things like it's always going to be lead 2 plus 2 electrons goes to lead. Zinc 2 plus 2 electrons goes to zinc, right? So it'll always be with electrons as the starting material, as the reactant. So the not E cell, my goodness. The reduction potential for this one, and I just looked this up on the table, is negative 0.126 volts. The reduction potential for zinc is negative 0.762 volts, right? And so wait, I didn't want to do that. We're just looking this up in a table, right? So there's a table, it's got a whole bunch of values. You look it up, you plug those values in, and we're going to figure out how this goes, right? So all of that is whatever, that's fine. What we're going to notice here is what sign we want for our potentials, right? Because remember, our delta G, we want to be negative. That's the direction that's going to give us a spontaneous reaction. And so if we want delta G to be negative, the moles of electrons will always be positive. We can't have negative moles of anything. Faraday's constant is always positive. And so if our cell potential overall is positive, that means that delta G will be negative just because of this negative sign out here, right? So overall, come on, slides, give me what I want, right? We want, for spontaneous reaction, we need delta G to be less than 0, right? Which means that we need our potential to be greater than 0, right? So positive potential for the whole voltaic cell, right? So that means that we need to organize these two things in such a way that the overall potential of the cell is going to be positive, right? So we have a little bit of a problem because we've got two negative numbers. And what we're going to do is we're going to say that the potential of the cell is equal to the potential of the cathode, right, minus the potential of the anode. And so what this is going to tell us is, remember, we're always going to end up with a spontaneous reaction. So we're always going to end up with a cell potential that's greater than 0. We just need to put these two numbers in. When we figure out our half reactions, we figure out their reduction potentials, and we plug those in here in such a way that this gives us a positive number. The trick, right? The most positive potential, the most positive reduction potential will be the cathode. right? So if you have two negative numbers, the number that's closer to 0, in this case negative 0.126, minus negative 0.762. Right? And so the other one will obviously be the anode. We put this together, we get a positive value, we get 0.636 volts is the cell potential of our thing. And then this would be the potential that we would plug in to figure out delta G in this case. Now we don't really care what delta G is, which is kind of weird because we just spent all this time talking about how to calculate delta G. All we need to know is that delta G is negative. And so because delta G has to be negative, that tells us which one has to be our cathode and which one has to be our anode. And since we know how cathodes and anodes are related to reduction and oxidation, we know further that, here we go, that this lead reaction has to be our reduction because it happens at the cathode, right? And this zinc reaction, right, that is more negative is going to be the oxidation that happens at the anode. And so if we want to write this reaction in the forward direction, in the direction it's going to go, we need to have the lead reaction be a reduction, which we've done, lead 2 plus 2 electrons goes to lead 0. And we need the zinc reaction to be an oxidation. So we're going to go zinc 2 plus 2 electrons as products here. We sum our reactions together and we get this is going to be the direction that our overall reaction goes. And we know this because of how we calculate delta G. So if we were to then apply this to our voltaic cell, lead 2 plus, zinc 2 plus, and zinc. Here's our salt bridge, here's our wire, right? The electrons are going to flow from the oxidation, from the anode, to the cathode. Okay, so electrons will flow from the zinc cell to the lead cell. Okay. Couple of things to pull out of this. One, delta G always needs to be negative. That's our spontaneous reaction. And two, we calculate the potential of our overall cell by adding the standard reduction potentials that we get from a table in the correct way, right? And so that this formula is the one that you're going to use the most often here. Oh my goodness. This formula right here. This this E cell equals cathode minus anode. Get these reduction potentials from the table, plug them into this formula. That's going to give your overall cell reduction potential, and that should always be positive, right? We want that to be positive because that gives us delta G less than 0. Okay, so now we can actually see which direction our redox reactions are going to go when we know what our reduction potentials are. So that's useful.